Yeah, so let's start with the recap of what we've seen in the last. Sure. So last time we've seen Rossman's switching, and which is the Entropic Switching for DNS. So the general theme is to do with to study effect of random restrictions on various computation models. That is the context in which these lemmas arise. Right. Yeah, before that, we saw some applications of such lemma and the Hastad. So what we will do today is we'll see a inductive proof of this thing, switching, Rossman switching. See what this criticality is all about. And finally, going to proof of a paper which is on criticality of AC0. That's the session of today. Let's recall what is a Derandomization. It's a restriction or a partial input which sets each input variable independently to 0 with probability 1 minus p by 2, 1 with probability 1 minus p by 2, and leaves it star or unset probability. So what is the sampling procedure for obtaining such a restriction? First, sample a p-biased coin. Right. So it turns out whose head probability is p, and it's tail probability 1 minus p. And if it's tail, toss a fair coin. And this will give you such a random restriction. So today what we'll do is we'll see another nice way of another sampling procedure, which will be helpful for us later. So here is another way of sampling. Restrictions. A coupled fashion. So what you will do is first sample uniform string from 0 to n. Then this will call as assignment. And then an element from this box. This will call the times. So uniformly you sample a sigma from 0 to n. and cut out from this box continuously around them. And how do you obtain a free random restriction out of it? Again, you will say xi is star is y is less than p equals sigma n if y is greater than p. Yeah, I'm not going to argue this, but these two will give you the same random. And then you can define a random restriction rho sigma tau, and these two will give you the same distribution. So let's keep this aside for some time. We'll come back to this. Now let's look at the and again let's recall the notion of number elements. So we define the partial order one restriction. The prime is less than rho. If rho prime is obtained by setting variables of and then we have this notion of canonical restriction. No, I'm not going to go into the definition of this. So we'll use all these notions in the final code and modify them accordingly. So let's start with the inductive proof of Rossman's association. So what is the lemma say? That is a, let's say, or an and of you want to see it, then probability that the canonical relationship that just equal to 0 is less than some constant times yeah, so yeah, the inductive version of the proof uses dot closure. So let's see what happens. Let's unpack this statement. What does it mean to say that canonical relation period of F is T? So the way we define a canonical relation tree, there exists some initial clause which survived restriction, and then you query the variables in this star variables q in this and make it complete by written, and then plug in the zero class is the one, and we plug in the canonical relation zero at each branch here. At each branch here, we would plug in the canonical relation zero. Suppose there is a long path on canonical relation of length P. This is what it looks like. Roughly, there is an initial segment, let's say of length S in the first clause which you did, and inductively there is a segment of T minus S which is picked from the rest of the formula. So last time we actually opened this up further and we saw that we assumed that there are some R clauses which are involved in this one. I mean, you can just work with this guy and the rest. In fact, that is how we define our canonical relation. Okay, let's do that. Suppose the canonical relation is of the T. So there exists some S which is in this range. There is an L, the first clause which survives the restriction, and there is a subset of variables which got picked from this from the variables in S. This is just notation for sizes subsets from this set. We have and there are these two branches. Yeah, such that first thing is so this is just saying that the L is the first clause which is not killed by rho. So yeah, the way we define our canonical relation.
But it's not zero, it's actually one. Right?
Yeah.
Equals one.
Everything before L became one, and L is the first carrier survive. And equals VL is the variables in here. And another things. Yeah, if canonical relationship of F with respect to rho has a path like P, then there is some clause which is indexed by L, which is the first clause which is separated. And there is a subset of variables in that clause which got picked. And the rest of the formula has a canonical relationship, has a path of length T-6. So yeah, the nice thing about it is this is something which we can assume using induction. So let's do that. Might be back here. So yeah, so the probability that we might bounded by this huge union bound. Yeah, so by pi and pi is just a string for us. So this is just the variables in Q set accordingly. So yeah, this event implies union of a bunch of events. So by union bound, we are able to write
Aren't they disjoint? Why are they not disjoint?
fine. Okay.
So what is S?
So S is the segment which is coming from the first clause.
Right. So if one holds, the L is defined, right? L is simply the first. Right, so probability that one holds, then L is uniquely defined.
Right. Right. Okay.
So that probability math is not shared with another else.
Yes. Yes.
Okay.
For each row, you can tag it with S with this tuple, and yeah,
Oh,
a particular row doesn't get different.
Doesn't get two different tuples, right?
I mean, in fact, there's an algorithm for discovering what this S, L, Q, and pi are.
Is it just equal to the sum of this? This probability is like this probability that I choose a row and I find that I have 1, 2, 3 for this particular S, L, Q, and phi.
I think SLQ are like disjoint, but pi could be correlated. So like a pi is not a function of rho.
Oh, I see. Good. Okay. So it's union bound on S, L, and Q, but not on phi. Because there could be right. No, but the event 3 Well, you're saying that the same row, or what is it? Slide on. I want to make sure that. So when do you double count?
Let's see.
Once. So there is. You mean there could be a row for which two different pies? I think that's it. So there could be a row that's and there's this L, S, L, and Q which are associated with this row, but for two different pies. The decision tree, the canonical decision tree depth of F for that pi is equal to T minus S for both of them. And in that case, you are counting the probability of this row twice for these two different pies.
Right. Yeah.
Gotcha.
Yeah, this could be the two paths here. Yeah, so now let's look at these three conditions. So now let's try to factorize this. This one. And this will be famous. Okay. Yeah, this won't work because we haven't used down closure. Right. So yeah, yeah. So what is the first condition? First condition is right. Okay. So ideally, you would expect to get you would expect to get P log n or P minus 1, P minus S factor from here. You would expect to get P bar S factor from here. So this kind of saying that some S variables in this particular clause are getting becoming stars. And
the others don't matter because they're discussed.
Which one? For the first one. Yeah, and together with the summation, we somehow wanted to bound using bound. Yes. That's what we want. Right. Yeah, that's what we'll be doing as well. Yeah, so yeah, in order to appeal to induction, this is not quite in the form which
More or less, right? Because I mean, if you just do that, I mean, more or less.
yeah,
Because you still have the sum, right? So
it's conditioned with these two quantities. So hypothesis doesn't have that condition.
again.
So yeah, this is three condition on 1 and 2. So yeah, our induction hypothesis will not, as of now, doesn't have this.
What I'm saying is that it's more complicated because you can't just get p to the power s outside of the sum because it depends on s, right?
Yeah, we're not going to do this. We're not going to do this.
That's yeah.
Yeah. Okay. Right.
Right. I'd say morally that's what you think of as the contribution of each part.
Right. Yeah, but you could combine this with respect to the t minus 1 and then the
T comes out, but then you have this thing times the log n to the t minus s, and that's what you want to show that's at most log n to the t, I guess.
Yeah, so yeah, here's where conditioning comes towards. Let's look at this initial distance. What is this? We can one and two. Further condition now will come from some now close. Looks like.
You see that?
I mean, that board seems a bit more out of focus than this board. All right, yeah. Yes.
Okay. Now you're thinking of the same probability, but now where rho is restricted to come from some downward closed set f.
Yes, here again,
By induction?
it's not downward close, but we'll
Oh.
partition it into downward close sets.
Okay, so how did that go then?
Okay. So
Now we fix the particular L, S, and Q. And Q, right? And pi. So I fixed all of those. And for which 1, 2 holds. Isn't rho, don't you actually want that rho composed with pi goes into Q is now in this set F, I guess? What?
sorry. Okay. Sorry, I didn't.
So now to use the induction hypothesis, you're not going to use it on rho, I presume. You're going to use it
Yeah.
on rho except
Except for the variables in Q.
right? Which is sampled by the same thing, right? Because you've set those variables and that's it. So now you want to look at the set, which is not F, but rather the things that are in F, but where the things that are in Q have been fixed to pi.
Yeah, so
Is that now downward closed?
this is a downward closed condition. And setting more variables in rho will not change this.
Ah, yes.
But this is not a downward closed condition.
Oh, I see.
Yeah, there is a small trick which you do here. Instead of working with these three conditions, I mean, suppose you further ask in order to make it downward closed.
No, but aren't you going to fix all the variables in this clause? CL to something,
Yes,
right? But once you do, then, I mean, that condition doesn't. Mm. Right, then that clause will be fixed to something, presumably.
All right.
And presumably a 1, because if it was a 0, then the path would close, would finish, right?
Mhm.
So when you sum over pi, I presume pi is actually only over the settings of the variable in that clause that don't set it to 1. So it's not just any pi, right? The sum that you have.
But this condition 2 is still lurking inside. And that's not a closed condition. I mean, what we say instead is whereas this is a normal closed condition, CL restricted to rho with Q restricted to
Pi?
sigma
Oh, sigma.
is 1.
Oh.
So is 0. Rather than saying that CL survives rho, we say that CL is the first clause. CL gets killed when you set Q according to.
Oh, and that necessarily means that it can't be 1.
Yeah, that necessarily means that it can't be.
So now, okay, so now you must take a row such that if I additionally set the variables q to sigma, this clause remains 0. This clause equals 0. I mean, but
So it okay. Oh, you're setting to Q, so Q is not set by row. But
Yeah, so at this point, when we're analyzing this quantity, we have fixed SLQ and pi. And given a sigma, let's say it doesn't hurt us to carry a sigma now. Doesn't change anything. I mean, in the final answer doesn't change much.
okay.
Yeah, so let me just change it to
Well, yeah,
at this point we haven't defined
we have to do it on part 2.
Yeah.
You take clause CL and you set.
Let me also get to this.
Now you set the variables that are in Q to sigma, this clause becomes 0. Okay. And that's downward closed condition.
And that's closed on this set of elements. And you use induction to get this moment.
So that means that F intersect, right? So
Right.
if you take F intersect with this condition CL, right? Let's call that F prime. Can you call that F prime? That's the clause of prime. Yes.
Concatenated with
No, F prime is just the clause of those partial assignments, such that if I append Q, set Q to sigma to this assignment, CL becomes 0. Right? Let's say that that's F prime. And now we can look at F. Oh yeah, no. I think I got it. So your new F is going to be the set of rows, which are assignments. The clause, you're missing the clause. CL.
Yes.
But also with row. Right? So I think your new set F prime is a set of assignments to n minus q variables. Right? So F prime is contained as 0, 1 star to the n minus q.
Right.
And now it's a set of those assignments such that if I append them, right? If I set the variables q to sigma, the clause CL gets 0. And if I don't set those variables, right? If I don't set these variables and extend and set q to stars, I get something in F. Right? That's what you want. Your new F should be that.
Yes.
Can you write that down?
So the values F and the section.
It's not exactly F, right? Because F is a set of assignments on n variables,
Right.
whereas F double prime should be a set of assignments on n minus q variables.
Okay. Okay. F prime is on n minus q variables.
Right. So is that double prime, yes. I mean, you can only intersect things that come from the same universe, right? Can you just write it down so that
Yeah.
so it's clear?
Yeah, the final downward close set is this is also coming from.
Can I write what I think?
Yeah.
What I think should be there? Let's say that this is the final. Okay. It's that, let's say row the prime. Such that they row of the prime instead of the variable in q to sigma. I have the clause CL 0. Right? And if I take row of the prime, we set the variable q to stars. And this is what right.
So
And this is downward close, right? It's set at downward. Right? Right? I take a thing which is an assignment to all variables in set Q. I can extend it to an assignment of all the variables by setting the things in Q star. If I do, I get something in it. Now I claim that, well, this set is downward closed, obviously, because I've set every variable here, so I can't change the variable above by setting more variables. And look, if I take the row double prime, right, and I set more variables in, right, when I compose with Q, if the original row double prime was an F, when Q's are star, by setting more of the other variables, I get something which is studded. So this is also downward closed.
So F is just coming from the conditioning on top,
Yes.
and we're trying to, this intersection of these two sets written below is supposed to be the new set we're trying to condition on in the induction.
Yes.
Okay.
Yeah. So induction hypothesis is for any arbitrary virtuals.
Right.
Yeah. So good for this. So yeah. So yeah, all this is to justify that you would get a using induction hypothesis, you would get a p log m power 2 minus this. You can probably put a better bound here, like m minus 7. This would do.
M minus n.
Yes.
I mean, the size of the rest of the formula is actually m minus l, not.
Oh, m minus l classes, yeah.
M minus 1, no? Isn't n the number of clauses?
Yeah, m is the total number of clauses in this. But here, essentially, you're working with the remaining formula after L.
Oh, I see. Yes. Okay.
Yeah, but this would do.
I see.
Yeah, so. Yeah, so and now let's look at the second condition, which is yeah, so for this, what you would do is similar to the what we did in the Hastad rule. You would define a for each row, you would define an enough row and set the variables in Q to a particular assignment.
Oh,
So enough row is
number of descendants of row.
yeah. So, but in the star locations, you're allowed to either leave it star or set it to one particular like the. And that argument is going to give you a 2p by 1 plus p equal pass.
Oh, how much does it give? Can you write it down?
Yeah, that's just the same argument which we asked us. And now let's focus on this. What we left with is yes. Looking there. So this is just going to give a factor of 2 bar s.
Sure.
Yeah, so I'll just drop this and then carry this 2 bar s. And yeah, these 2 bar s are going to be absorbed and they won't bother us. Right? And instead of working with a particular Q, take the Q which maximizes this quantity. The Q star which maximizes this quantity.
But Q.
The condition 1 is a function of L, S, L, Q, and phi. Or rather, the way it's stated, the function.
I thought that now the probability was unique, right? I
I
mean, these probabilities of one are, they sum to 1 when you sum over all SLQ. That's what we said, right?
okay.
Maybe that's not true. Maybe that's not true. Oh, maybe that's just not true, actually. So, I mean, oh, no, maybe this. L is uniquely defined, right? L is uniquely
Yeah,
defined.
it is uniquely defined. Q again is
Oh, but now I see. Okay, so they sum to 1, but the value that you're averaging depends on S, actually. And let's say the P is taken care of. So you have P to the T outside, and now. Right, so now the only thing, so you can get rid of the L again, I suppose, and now you're left with the S. And that's it. S, no, can you get rid of the L? Wait, why can you get rid of the Q then? What are you saying?
No, I'm not getting the Q. So I'm taking the maximizer and then
The maximizer. I mean, from my understanding, you have now P to the S outside times 2 to the S maybe, or sorry, P to the T outside.
right.
P to the T is outside, and then you have a sum over all S, L, Q, SLQ, some probability, right? Times 2 to the S times log M to the T minus S.
Mhm.
And the whole thing you need to show is at most log M to the T. Right? I'm ignoring this 2 over 1 plus P or something.
Yeah, just you can say here given that it's upper bounded by
Yes, let's say. Good, then you get, I mean, okay, so then you have, right, good. So then now the P disappears, right? So because the
Yeah.
P is done. So it's P to the T outside. Can you write it? Just so.
Yeah.
Now there's some P to the T outside. And it's a sum over SLQ. Oh, by our arguments, it's going to be this probability of 1, right? And then it's 4 to the S, which is kind of what we're accumulating. And it's log M to the T minus S. And this quantity, you want to upper bound by log M to the T.
Right.
Unless, is there a 4 also before this log M that was kind of, that you didn't write because you weren't bothered? There's some constant, yeah, like 2e that was there. So now you can actually assume there's a 4 inside by induction hypothesis, right? 4 to the T minus S.
Yeah.
And that moves the 4 to the T outside. So now the whole thing you need to show it's at most log M to the T. And if you can show that, then you're done.
Confused about that comment which you made. Summing up to 1.
Yeah, it's summing up to 1. So it's an average, but it's an average of things that depend on S, right? On S, L, and Q. Right? You have to show that this average is at most the whole thing.
Uh, yeah. Right, we can just up on this by okay. The reason why this thing won't sum up to 1 is this cube. I mean, if you had condition 1 along with 2, then this would have summed up to 1.
Oh.
I mean,
Oh, I see. Yeah, yeah, okay. Oh, I see what you're saying.
this is just this doesn't have any cube inside.
Yeah, yeah, okay.
Right. So yeah, so that summing up to 1 is not true, but this is true. Summation over L, summation over L probability 1 is answer. Yeah. So, yeah. So there are at least there's possibilities for Q, and right.
Oh, and that's log n at most to the f log t to the s or something. Or sorry, t to the s, t to the s.
Yeah, this is T to this. Yeah, that's what we're going to use. Probably. Yeah, let's safe and let's be safe and write it as required by this. Yeah, so that this is the quantity we're interested in.
Where did those?
I just replaced
Oh, okay. Oh, I see. So it's a tighter round. Okay, so. Okay.
Yeah, so here is something. Here's a nice trick. Okay, this is nice. This looks like expectation of some guy. Right. If this was concave, I think this would be going in the right direction.
Oh,
But this is not going. I mean,
it's convex at best. If S is all, is otherwise it's neither or. Well, you don't know what S is, right? So, but I mean, it could be convex, but it's not.
yeah, this is convex. T bar S is convex. If this was concave, if we had a concave function here, we would have this inequality would be going in the right direction. We don't have a concave function there. Here's a nice trick which coming from Rossman's paper. This is write it as log of 2 pi 2 parts. And log par s is a concave. Yeah, so one is just trickery with calculations. I mean, there's hardly any teaching in what I'm doing. And yeah, so now we can use concavity of log par s.
So the average of the F. Okay. So the average of the F, if its function is bigger than the.
Yeah, so this would be less than log of the party times.
Wait, if a function if the function is concave, then F of the average point is bigger than X. F of the average point is bigger than the average of the points. Yes, okay, good.
Yeah.
Fine.
Yeah. And now my claim is that this probability 1 is roughly 1 by 2 power t. Let's see that. So what does probability 1 include?
Oh. I mean, they all need to have been set to 1 before.
Right.
For that to happen, because they are ORs, it is at most 1 over 2, no. It's at most 1 over 2 power t, right? You want to say. It's like all the clauses have at least one variable. So, oh.
Okay, so it's not exactly coming from this statement, but yeah, so it's coming from the 1 by 2 part is actually coming from this. So
No, but we're only looking at 1, right?
yeah.
Right, so what's the probability that L is the first clause that hasn't been set to 1?
No, that would be okay. Okay. Actually, let's write this as condition 1 because you need this condition to get 1 by 2 party upper bound on. This is actually saying that rho. So real is the clause we understood. CL is a clause we understood. Some S variables are left unset in that. So, what is this T? T is just the size of the clause, not real. Yeah. So this condition is just saying that rho is setting. Yeah, there are S stars in rho, and everything else has to be set in a specific way for this clause to not get hit.
S are
I mean, if any of those variables are set to 1, yeah, so the CL looks like an OR of a bunch of things.
yeah.
So any of them is set to 1, it would have been killed. So the fact that it survived means that they're all either set to 0 or set to stars. Some S of them are set to stars. So that means VL minus S of them are set in a particular way.
Yes, VL minus S is set in particular. I see.
And that happens with probability 1 minus P by 2 whole power VL minus S.
Yes.
And so this number is upper bounded by
How about the other ones? You can now use that part of the board still because the camera is shifted. So you're saying that the probability that this happens is at most 2 to the L? No. 2 to the S divided by 2 to the size of the L. Okay, so this log here is
this
that
product
log
is going to be just to the S.
to the S, yes, to the S.
To the S.
So the log is at most F. And so you get there S to the power.
The summation is over. So this will be
Oh,
log n.
oh, I see, that's log N at most. I see. So you're saying that inside the summation is at most N times 2 to the S, N times 2 to the S.
Yeah, so it will be
Log of N times 2 to the S, which is at most S times log N.
yeah. This is almost S plus log n.
So S plus, yes, S plus log N. Almost what we want. So you're
Yeah.
saying that you throw away the S now?
Yeah.
So this is at most, you're saying e to the S times log N to the S. Is that it?
This is just
No, can't repeat the, I mean,
sorry.
sure, okay. Which is at most log N plus 1, which is fine, let's just say that. Order log N or something. Okay.
Yeah. This, right. So I completely messed with the calculation. So yeah, so the idea is to break this into events of this kind. So one is to look at the first part, then and the rest. And there are 3 events which are happening. One is that a section of the long path is coming from the first part, and some q variables are stored in that the first part, and the remaining part of the long path is coming from the rest. Based on these 3 conditions, you can factorize this product into 3 parts, and these are the bounds which you get on each of the parts, and somehow using some convexity, you can bound these 2 parts separately, and using some convexity, you can. Yeah, this is an alternate proof of what we saw last time. Last time, what we did was we constructed this huge tree of choices, and then said that the size of the tree, bound on the size of the tree, is will just give us a bound on this number. Yeah. Okay.
Okay.
So now let's now that's done. Let's move to criticality.
Right.
So what is criticality? So Boolean function f is lambda critical. So you apply a random restriction on it. This definition is completely inspired by switching lemma statement. F is lambda critical.
T, that's T, not the S.
Ah, yeah, and you can define criticality of a function as the smallest lambda for which it's lambda critical. Yeah, so why are we bothered about criticality? So it has some nice implications. In the first lecture, we saw that switching lemma implied average space lower bounds, right? And yeah, so many of the consequences of switching lemma turns out are just consequences of a statement like this. Yeah. So F is lambda critical. Then implies you can give bounds on different size of F.
At least.
No, our bounds on the different reasons.
So you go from a statement where the probability of F having small decision trees is
F has small decision trees with high probability. Small decision trees with high probability. From that, we are implying that
probability that F has large decision trees is small, and from this it implies so that the decision tree, the actual decision tree of F is not very large. Right.
And yeah, it's the construction is not. I mean, it's nice in the sense the way you would construct a decision tree, the way you would go from constructing a decision tree from a criticality statement is
you choose a threshold, and now you know with this restriction is small, and for the rest we do brute force or something. Is that something? But you choose the right P.
Yeah, choose the right P. So what you do is, I mean, you start with some 1 minus P times n variables. Just completely make a binary tree or complete binary tree of them. And then you analyze what the sizes of these things are. The size of a decision, here is a way of constructing a decision tree. Right? You pick your favorite 1 minus P times n variables, query them completely, and then for each choice of these queries, you want to attach a decision tree.
Smallest possible decision tree.
right? The way switching lemma is going to come into the picture is switching lemma says that if you apply a random restriction, the decision tree depth is going to be small. So going over all these children is like picking a random child here is like applying a 1 minus p times n random restriction. And that is going to say that a lot of these children are going to be short. That
So the
would
total
mean that their sizes are small.
Okay.
And very few of them will be large, but how large can they be? The worst case bound, and that would be
Right.
In fact, this is also how you get satisfiability algorithms for from this statement. This would give correlation norm. Yeah, the proof is exactly what we did in the first lecture. So in the first lecture, we saw correlation for DNF. Following that, you will get that criticality implies correlation norms. And there is something else which if we are interested in, which is called the degree criticality. So which is
Measured in terms of degree instead of decision tree.
yeah. So here we are interested in decision tree depth after a random restriction. So you could ask what does the degree become after a random restriction? And since if you have decision trees can be easily converted into polynomials, you have a depth T decision tree that becomes a degree T polynomial. So from that it implies. And then more interestingly, you get Fourier train norms, both on L2 norm and L1 norm.
What's that K? K.
So that's the K. And as well as yeah, these are the kind of bounds I think.
That's a big O.
Yeah, that's pretty good. Yeah, these are the bounds of L11 or I think for various classes of functions, I think it's interesting to see what these bounds are. Yeah, so criticality bound would imply all these things. On top of that, you would also get satisfiability algorithms. And it turns out for
You mean you
AC0
get
and
faster than exponential satisfiability algorithms for F?
yes. A decision tree of this size would
Oh yeah. Oh yeah.
yeah, but also you need to construct this decision tree in small time. But it turns out the construction which we discussed does it in small time.
Okay. All right.
Yeah. Okay. Yeah, those are the implications of criticality. It turns out for AC0 formulas, for AC0 circuits, all these are tight. The bounds which you get out of criticality are
So I should think of criticality as a number between 1 and n. Is that's
Yes, that's
roughly?
true. That's true.
Because I mean, it's not obvious a priori what that is the case, but
Yeah,
it's from the definition. I mean, but I could think of it as some kind of number between 1 and n.
Mhm.
Okay, and if the number is small, then the function is simple.
Right. Maybe, I don't know, maybe you can think of it as a tail bound. So if you have n variables, if you apply a random restriction, you expect some pn variables to survive. That's like an non-adaptive statement.
It's 50 and there, yes, to survive.
Pn just and yeah, and yeah, this is, you can think of it as an adaptive version of that.
Oh, I see.
Okay, so here are some known classes for which we know criticality bounds. The first thing is every function is analytical. And in fact, if you take a random function, its criticality will be, it's expected to be, and yeah, so for depth decision trees, again, criticality is A. For parity, criticality is M. And the Hastad switching lemma will tell you that with W DNFs or CNFs, criticality is order W. Rossman's switching lemma tells you that first type this DNFs. Criticality is order W.
Log S.
And yeah, here's something which we haven't seen, but it follows from Hastad's multi-switching lemma. Say that AC0 set is the criticality is log this part.
This, oh, we kind of did this, no? This is what, isn't this what we did on the first?
No, we just showed that we just showed a worst case bound. Criticality implies average case bounds or correlation bounds. In the first lecture, what we saw is just a worst case bound.
We did the average case.
No, we said we used a union bound and that was very lossy.
I see.
Lemma.
Ah.
That is the first time where this correlation bound was shown.
I see.
Such good correlation bound. There were correlation bound before.
Okay.
Yeah, this is again restatement of Rossman. It was not originally stated in this way. Yeah. So, and finally, the conjecture is to show that AC0 formulas have criticality. Always by the
And that implies like all.
and that implies all of us.
Yeah.
Yeah. I mean, the conversion from circuits to formulas will tell us that this statement implies this. And DNFs are again some depth to formulas. Yeah. Yeah, and look at that.
Good. And that's what you're going to show us
Yeah.
for the rest. So all this up till now was preparing us for what you're going to show us in the next hour or so.
Okay, so yeah, we're going to need some of these notions which we've seen so far. So what are these? So I'll just say this. So far we've worked with DNFs, right? And our first attempt, and when we work with AC0 circuits, we again took DNFs and applied switching lemma to them, and then the union bound. Right? Yeah, but how? So here, what we would do is
So
come up
that's
with-
what you do for circuits. Is this what the multi-switching lemma allows you to do or something?
so multi-switching lemma, what it does is it comes up with a hybrid object. It also gets around union bound. So what it does is, when you're given a circuit, it constructs a combined decision. So suppose you have a circuit with a lot of DNF sitting or CNF sitting at the bottom. So it constructs a combined decision with all these DNFs. So the common decision tree will look like a common part, after which each of these becomes a small decision tree. All these right.
Oh, okay. But not, okay, not necessarily the same. I see.
So yeah, so you're not doing a union bound.
So you simplify all the CNFs by a single set of queries. And once you've done those set of queries, all these CNFs and DNFs all have simultaneous small decision trees, which of course could be different. between them.
Yeah.
I see.
Yes.
Okay.
These are each lead. At each lead, each of them becomes a very small. Right. And then
And then you continue.
you continue this way, then
You flip and continue.
you flip, and then you do this process again, you accumulate these common decision trees, and finally you would end up with
A single decision tree that made the function pass. All right.
yeah, this is again another clever way of getting around.
So why doesn't this work with formulas?
Why does this work for circuits?
This works for circuits.
This is for circuits.
So why is there no hope? I mean, why is it a priori not obvious how to
Sorry?
use it for formulas? Because the technique itself is going to work for circuits always.
No, okay. It does work for, I mean, formulas are certain kind of circuits, so it does work for formulas, but you don't get as strong.
Yeah.
The fact that it works for circuits should mean that
You need a different approach for
Yeah.
formulas because you want a better bound.
you're,
Okay.
yeah, if you got a logism by D for logism equal to pi D for circuits, that would be not true.
Right.
Yeah. Right. Yeah, so the approach here is to construct a canonical they should be for a formula at 1 over.
So, okay, sorry, but before that, it's not obvious for me. So why is the criticality for circuits the best you can hope for? Why is it,
Why is the number log s
log
power
to the
d
power d,
the
yeah.
best you can hope for? Um,
Maybe, can you compute a parity faster if you have a circuit? Or with smaller circuit than a formula, actually?
okay. Let's see.
Yeah, but that's too complicated.
What it looks like. Right? This is the agreement probability.
Yeah.
Let's try to make this 1.
Okay.
Right? But in order for this to be 1,
So you want to compute the parity, saying.
yeah. Yeah, when n plus 1. Yeah, for that to happen.
Yeah, so you need a circuit of size 2 to the n to the 1 over d.
Yeah. When x is 2 to the n power 1 over d, disadvantage is 1. Suppose you had a stronger bound here.
Right, but the point is that, so you're saying you can do that? So you can do parity with circuits of size 2 to the n to the 1 over d. Because it should be obvious that there's a formula of size 2 to the d times n to the 1 over d. Right? N to the 1 over d. And that's by taking parity of width n to the 1 over d. Right? You just take a single parity of width n to the 1 over d, and you do a formula of depth p for this. Right?
Yeah.
A formula of depth p of these parities. Right? There might be a p minus 1 there or something. But let's ignore.
Yeah.
But that's a formula, and what will its size be? Well, it'll be 2 to the n to the 1 over d. That's how much it costs you to do each parity with the CNF, right? And now you compose all of these. Maybe that should be there. It should come from this, right? It's
Yeah.
formula, right? So what's the size of this now?
Yeah. So what is the size of this construction? What are you talking here? So you partition the variables into chunks of size n bar 1 by 1.
Right, and you compute the parity of each, and now you partition those.
How are you
into
going to
chunks.
make this? Recursively or?
Oh, CNF.
Oh, CN.
So then the size will be,
Ah.
then the size will be to, is it 2 to the gn? Or no, what is it? It's 2 to the n to the 1 over d. Maybe
And then there are
times n to the 1 over d or something, times n, let's say. Right, each. Okay, how many are there? It's this.
and then you have to combine those as well.
Right, you combine those, you group these in chunks of n to the 1 over d size, and you do it again, and you need d layers of that.
Yeah, okay. But
No,
is
why,
that
why is there a d there? Why is there a d there? Oh, I see. Oh, I see, because it's the thing to the power d. Perfect, that's where the d comes from, right? Oh, is that perfect?
no, is that a circuit or a formula?
No, that's a formula, that's a formula. Oh, and you're saying
When
the circuit, you can say. I think I see. Yes, I see. I see. Okay. I see. So with the formula, so here's the thing. So these formulas, these DNFs that you're using, they have that size, which means they have that number of inputs. Right? Now, if it's a formula for each of these inputs, you need to repeat the whole subtree.
Right.
Right? So the size is 2 to the n to the 1 over d to the power d. Right? Because it's like this, right? Right? Right, so you can do n to the 1 over d. Now each of these gets implemented by a DNF or a DNF. That's the trivial one. Now the size of each of these things is 2 to the n to the 1 over d. Good. So now you group it again. Now you take n to the 1 over d of these blocks, right? Each of them outputs 1 bit. And now you're going to compute a parity of these again. So now here comes the difference if you use a circuit versus the formula. Right? So now you're going to use the same CNF to do this, thing. So it's like, or maybe you flip so that so it's like an and or. Now this has size 2 to the n to the 1 over d again. But here's the thing. So these ors, I mean, each or might use these multiple times, right? So the fan out here is big actually. So if you have a formula for each of these input bits, you have to repeat this entire thing. So if you're measuring this, right? So in total, you know, this is the number of inputs roughly. Right? So for each of these inputs, you have to repeat the entire CNF. So the size of a formula is 2 to the n to the 1 over d to the power d, because it's a depth feature. Right? But if it's a circuit, although this formula is of this size, you don't have to repeat the inputs these many times. Because once you've computed it, you can use it as many times as you want. So instead, you know, it's the sum over the number of these blocks of 2 to the n to the 1 over d, which is roughly 2 to the n to the 1 over d. So the circuit is actually less small. Okay, so now I understand this.
Yeah, I mean. I hope this is clear that if you get anything better here, that would mean that would violate that.
Sure.
Yeah, parity.
So, yeah. So the criticality is at most.
Yeah, criticality cannot be more than
Log acidity.
log. Cannot be less than log.
Cannot be less.
Cannot be less than log. Yeah, okay. So yeah, so the idea here is to construct a canonical relation tree for formulas. So how do you go about? I mean, we have seen a canonical relation tree for DNS with respect to a restriction. Right. So the input here is a DNF and a restriction. So how do you go about constructing the canonical relation tree for formula at one go? I mean,
You told us, right?
sorry,
You told us, right?
No.
Right. Oh, for
DNS I've told you. For
oh,
formula
for
at
general.
one go.
Oh, I see. I see.
So here is what you will do. There are several items, but what works is instead of working with one restriction, you work with a tree of restrictions. This is again something. So from now on, everything with a tilde is a tree like object. Okay? Row tilde is the restriction for each node in the formula. That is the restriction. So what is the restriction tree? Restriction tree is it assigns a restriction for each node in the formula. And I used the notation for things
But then must the children be sub-restrictions?
with a specific property. Right? Yeah. Each,
Oh, you're just giving us the overview. Okay.
Yeah.
Sorry. Definitions will come.
Yeah. Oh, no, okay.
Are you going to define it later, or should you either define it, or are you giving us an overview, or are you going to define it?
I think I think.
All right, then you don't have to define. Okay, so there's
Yeah.
these three restrictions.
Yeah, tree of restrictions is something, it assigns a restriction for each node in the tree, such that the parent is a refinement of the child. I mean, the parent's restriction is obtained by setting more variables of the children. And there are several children, the parents has to be consistent with all of them. Right. So that is tree of restriction. Now again, the question is, how would you sample a random object of this kind? So it seems very complicated, right? So you want to sample a restriction for each child, such that the marginals are like RP, but still they're consistent.
But should they be RP for different P's?
Yeah, for different P's. So then the question is,
The point is that, I mean, these restrictions, they compose well or something.
sorry.
Right, because you have this property that RP equals RP1 times RP, composed with RP2
Yeah,
or something.
yeah.
Okay,
Yeah, so what is the random tree restriction? Okay. Yeah, so suppose you are given a tree of parameters P tilde. So previously we had just one restriction, so we had one parameter RP for RP. So now we'll give a parameter for each node in the tree, such that again parents parameter is less than the child's parameter. That looks like this, or of a bunch of things. Parents parameters. That means there are fewer stars in the parent.
and you're going to choose, so if I is the child of what? Oh, I see. And then you choose with what? One divided by the other or something.
Sorry.
And then you choose the new restriction as one divided by the other. Right. Right. The stars that you haven't set, you now restrict them according to RP of this node divided by RP of the parent or something.
Yeah, but again, they should be consistent, right? I mean, restriction has two parts. One assignment and yeah, some of these variables are revealed here. Some other variables are revealed here. I mean, the revealed part should be consistent.
Oh,
Among
the different, oh, I see, they have to be the same among the different parts of the formula. I see. Oh, that's not obvious. Okay.
Yeah. Yeah, that is just to make it more complicated. The way to do it is using this kind of sampling. It gives you a coupled way of sampling all these restrictions. So the way you would do is again, you sample a assignment and a timestamp. Just that instead of specifying one key for the entire restriction, you would specify a different threshold for each node in the format. Okay. Okay. Random tree restriction. It is parameterized by just sigma, tau, and p tilde. P tilde is so this refers to the formula tree of the formula. We know that this is an assignment. This is coming from the box. So this specifies the random tree restriction. So you sample this uniformly, and for a given choice of parameters, that already specifies a restriction for each node, and we can verify that it satisfies all the consistency properties.
So then I should interpret the p tilde restriction as saying that children become defined at a later point in time as the parent, or something like this. Right, so I can think of this p, what is it?
So P is a threshold. P is a threshold parameter which gives rise to a RP restriction. So at the end of this, if you sample these things accordingly, you would get for each G in the formula tree, RP the restriction corresponding to the node G is obtained from R p tilde of G. Yeah, so this is, instead of working with a random restriction, we'll work with a random tree restriction. And the next thing is, so previously we had a canonical relationship of a formula with respect to a given restriction. Canonical relationship of a DNF with respect to a restriction. Now we will have a canonical relationship of a formula with respect to a tree of restrictions. So I'll get to that in a minute. Yeah, so there's nothing randomized here. You are given a fixed formula, fixed restriction, and you are outputting a different. Similarly, you are given a tree of restrictions and S0 formula, you would output it as different. Let's see. How to construct canonical relationship of S0 formulas. Suppose you have a formula look something like this. It look like and of I'm ignoring the corner cases. Like suppose if it's constant or if it's a variable, then we can. Right? Suppose the formula looks something like this. So what would you do? Find the first child, like that. Next by that. FL is referred to within the rows F. So basically, each node in the formula tree is associated with the restriction. You would take a parent's restriction and
These
scan.
are all consistent, right? So it's any variable, and the assumption is that, so because I hadn't understood this. So what's a tree restriction?
Okay.
So it's a tree because you still haven't given a formal definition, right? So I have a restriction for each node. And if I have a child, then it's a sub-restriction, or it restricts more variables than the parent.
Mhm.
And whenever a variable is restricted, it must be restricted to the same value everywhere,
Right,
right? So these are the three conditions.
right. I mean, the third condition is, I think, follows from the second. Each,
No, it doesn't.
okay. Mm,
I think I have a single variable, the parent is a star, one child is a 0, the other child is a 1.
right,
It's like,
right.
do you get
Yeah.
more restricted as you go up or? Oh, okay.
As you go up, you get more restricted.
No, you do, more or less, so I don't understand.
No, as you go up, more variables get set.
Oh, as you go up, more variables get set. Oh. Oh,
Fine. Yeah, so the situation you said, okay, one child has a variable set to 0, another child has a variable set to 1. I mean, okay, the issue there is the parent has to be set. Fine. That cannot happen because the parent,
so then I thought, I was thinking of it the other way around. So as you go up, more variables have to be set. Well, then yes, then it falls from that. Yes. I see. So in particular, all children are compatible.
With each other, yeah.
I see.
total F is obtained by setting more variables.
Okay, but then can we? But then isn't it the other way around? No, so if P is bigger than. But if P is bigger, then I have fewer variables constrained, right?
Right,
So in a tree of probabilities, it should be the other way around, right? That the P of the parent is smaller.
yes.
Oh, that's what you written. Oh, perfect. So the P should be smaller so that more variables are set. Okay. So now I understand. I was thinking of the whole thing the other way around. All right. Okay.
Yeah, this is, I think, this defined. Yeah, this defines three restriction. Yeah, so let's continue with the algorithm for constructing a canonical dictionary for AC0 formulas. Just like in the CNF case, you scan from left and see what is the first child which is not becoming 1. But there you have only one restriction row. So you went to each of the children, applied that restriction, and asked whether it became trivialized or not. So here, instead, what we would do is take the parent's restriction and then go to each of the children and then ask which is the first one which survived.
Sorry, what is the issue?
So rho tilde of f, rho tilde of is we are associating a restriction to each of the nodes in the formulae. Rho tilde of f is the restriction associated with f. So you are applying rho tilde f to each of these children, and seeing the first child which survives that.
Right.
As opposed to asking, another way of doing this, one can think of is just ask, take F1, apply its own restriction to it, and then see if it survives or not. That could be another way of defining it, but that's not what we're doing. You take the restriction of the parent and then scan from left to right, and then see which is the first one which survives. And you would take the canonical dictionary of that surviving guy with respect to the subtree of restrictions. Okay. Root tilde restricted to this subtree. Right. This is a tree of restrictions on this subtree. Let's call this gamma.
Okay.
Yeah. So previously in the DNF case, what did we do? We found a clause and built a complete binary tree of it. So here we do not have a clause. Here we have a subtree. We have a decision tree. Yeah. Previously we had a complete binary tree, and we attached that. So here one might want to just put this gamma.
Oh.
And then this is the naive attempt is to put this, and then for each one leaf you recurse. That's not going to work, because complete binary tree has some nice properties. It's that, which we haven't noticed before, is that suppose there is a long path in the entire decision tree. There is an initial segment. So for every one path here, there is a corresponding zero path, which is unique here, and with the same set of labels. This is the reason, probably the reason why we redundantly queried more variables.
The reason why we want.
I mean, the decision tree for all looks like a code. Right? But we plugged in a complete decision tree in the canonical decision tree. Right? Yeah, one reason to think of is, suppose we plug in a code and we got a long path. Then this claim is not true, right? And here the claim is that for every for every one path, there is a corresponding zero path which has the same set of variables in the same order. Suppose you plug in this object and request. What and the long path occurred along something like this guy. Then you would have said, okay, the long path can be broken into several parts. The first part is coming from some CL1, but there is no corresponding zero path corresponding to.
Not of the same size.
Not of the same size.
Okay.
I mean, that kind of is what was helping in the encoding proof as well.
But I can take, but I can always extend the tree until all paths have the same depth.
Right. In the case of DNF, we achieved this by replicating it with a complete binary tree.
But I can always do that. I mean, not with the same variables, but I can, if I have any tree whose depth is at most t, I can always replace it with a tree of depth exactly t.
Oh, the issue is not just with the depth. We want these two paths to have the same set of variables.
Okay. Okay. So just tell me what. Okay.
Okay.
Because I can't quite.
So the property we want is
Hmm.
Right. So in the case of DNFs, we achieve this by taking the complete binary tree. So
remind, why is this important? Why is this?
it will become important later. We'll use it. It will become clear.
We've used it already. Okay, right.
We've used it already.
Right. So so somehow this zero path was the witness that this was the first clause, right, in the previous proofs. This sigma
Yeah. So
was a witness that this was the first clause that was set to 0 or something. Is that why?
Right.
That was not set to 1. I mean, that was not set to 1.
Yeah. Right. Yeah. So yeah, we want to identify the first clause which was not set by row.
Yes.
So we are somehow encoding the row. We are extending it by setting some variables such that the extended row sets this clause to 0.
Yes. That proves that this is a clause that was not set to 1.
Yeah. So
Right.
yeah, in the encoding proof, we needed these sigma 1 to sigma r,
Right.
which are these auxiliary 0 paths.
Right.
Right. Yeah, that inherently assumes that for every one path, there is a corresponding 0 path with the same set of variables. At least in the encoding proof.
Right.
Yeah, so we want to generalize this property for arbitrary trees. So here is a arbitrary decision tree. We want to massage it and get this property. So, right? Yeah, so yes, here you have a decision gamma which does not have this property. So what you are going to do is take any arbitrary one path. Right? It need not have a corresponding 0 path with the same set of variables. So what you do is you go up this tree. Fine. For all you know, all its siblings are also ones. Suppose
Siblings? I mean, what do you mean?
sorry.
Well, there has to be a 0, right? Otherwise it's been set to 1.
Okay, in our canonical decision tree for DNF, we were plugging in.
No, we found the first child that hasn't been set to 1, so there has to be some input that sets it to 0.
Yes.
So there's not just 1, then the 2.
No, yeah, right. There will be at least 1, 0 in the tree. But it need not be the case that the sibling of this is a 0. If this sibling was a 0, you found a 0 path which shares the same set of variables, which query the same set of variables. But that might not be true. For all you know, I mean, a huge subtree here is all ones. Is the tree we're interested in? This is the one path we're interested in. So what you do is go up this tree till you find a node which has a 0 path. Go up this tree till you find a node which has a 0 path. So what you do is once you found this node, right? So this is the one leaf you're interested in. You went up this tree and you found the first node which has a 0 leaf. So what you will do is at this node, just duplicate this. I mean, this is the all ones. Decision tree. I mean, for all you could also on this one input of one. And that will be the same decision tree. But instead, what you will be doing is you duplicate this decision tree here and replace all leaf nodes with one. Label all leaf nodes.
What? You do what?
You copy paste this left child here. And right. So
By copy, you mean you're just querying the same variable?
yeah, you're querying the same variables. But the leaf answers will be different. Here you had a different decision tree here. You just mirror this here, but answers of all these leaf nodes will be one. That is your, let's say you started off with gamma. Okay. By doing this, you would have obtained a gamma prime. So you do this for each.
No, sorry, I'm still not understanding. What do you do that? So you start with you look at any leaf
So
that is the one leaf. You find the first ancestor, the topmost, no, the lowest ancestor that has a 0 sibling. And then under this one leaf, you copy the tree.
yeah, so you find these ancestors. One of them has this guy you're interested in. The other one has a 0 path.
Yeah.
You just completely chop this off, and then you copy this tree here. Since this is a decision tree, so all of them should be labeled by one, of course.
Oh, I see. You're saying it doesn't matter. I see. So that should be a 1 there. I see. And then you replace this. Oh, okay. Ah, and that 0 is the. Oh, I see. And that 0 is the 1.
So let's do this process for the
Cool.
or tree or random tree. Okay. Say this. So we call this as one balance. What do you do? I mean, okay. I just described what you do at one leaf. So for the tree, how you do unbalancing is start from the bottommost depth leaves. For example, okay.
That's a bad example because the one
That's
does
bad.
have the one does have. So switch the one.
Yeah, we can do that.
Okay. The one leaves at this depth 3 are all balanced.
Yes.
Now you go to depth 2. Okay, we found a one leaf here. It's not balanced. Okay, you go to the first ancestor which has a 0 leaf, right? And you duplicate it here.
Right.
What do we get? And then okay, all the leaves at this level are taken care of. You go here. Then what is the least ancestor here? This one. You duplicate it. You get the complete value. It's a fancy check, but that this process in when applied to DNS is giving you another complete binary tree. So again, you do this one balancing operation. I hope the one at the end of all this, what the guarantee which you get is that for every one leaf in this tree, there is a corresponding zero leaf which queries the same variables. And that's sort of how you achieve this. Yeah, now we are good to go. Continue with this algorithm. Find the first child which doesn't trivialize according to the parent's restriction. Take its decision tree at its with respect to its with respect to its subtree. Okay. And then you one balance it. And suppose gamma prime is the one balanced version. For each leaf alpha here, for each leaf one leaf alpha here, you recurse for each one leaf.
Okay.
Okay, that is the construction. That's the algorithm for trigonometry. The input is the formula and trigger restrictions. And the output is a decision tree. So yeah, now let's yeah. Yeah, so again, this proof is going to be an inductive proof. So we are going to need some sort of downward closure. So now instead of downward closure for restrictions, we want downward closure for pre-restrictions. So the downward closure of pre-restrictions. Okay. Yeah. So now we want to define a partial order among the restrictions. So you have a tree, let's say root delta, and you have root delta prime. So when would you say that this is less than root delta prime? So in the case of restrictions, yeah, this is just component wise. I think of it as a vector of things, and think if it's when we already have a partial order for each restriction, if component wise this is less than this,
Okay.
that's just that's how you define partial order on tree restrictions. Once you have partial order on tree restrictions, you can talk about double closed sets. Okay. Yeah. Yeah, so that's how you define a downward closed set of tree restrictions. Now I think we are good to go. Again, let's follow the route of what we did in the case of DNF in the beginning of today. So we are interested in this thing. Yeah, let me define some new notation here. So given a string, suppose you are given a decision tree of that S and a string in 0 to the S, that will take you to a leaf in the decision. Right. A string in 0 to the S specifies a leaf in the decision tree. So it just tells you if it's a 0, take left.
No, I'm not confused. Sorry. What is S?
For any, I mean, if you have a decision tree of that S, a string of length S specifies the leaf in the decision tree. So for any S, what do we say? T for example. Here. What do I mean by this? This is the decision tree. TDT wrote is the decision tree. And A is just a path in this decision tree. This whole object is talking about a path in a decision tree.
Oh, that's the A path.
That's A path into the decision tree given by F. Again, another simplifying assumption. Instead of asking whether the decision tree has depth T, you can specify a string, particular string, let's say all zeros, and ask what is the probability that there exists a path along this, which is specified here. Instead of asking whether there is a path of length T, you're asking
Is also
is there a path given by this?
By this A. You're saying by union bound, that's like 2 to the T times at most.
2 to the T time T 2 to the T's are something which
We don't care about.
we don't care.
Okay. All right. So now you fixed it.
Yeah. So you're asking for a path of this shape. Okay, now let's do our unpacking. Suppose there exists alpha such that I missed something in the.
This is an alpha. What's alpha? Oh.
Suppose there exists.
Alpha 0 or 1. Is it or what?
Okay, this is a path or an ordered restriction. It's a tuple.
Oh, variables and values.
Yeah. Okay. So you can think of a path in the decision tree as a ordered restriction. I mean, even the order is important. Now this is over the story. Yeah, so sorry.
Okay, so there's a path.
You get a union bound with these also?
No, I think I messed up something in the definition of the canonical relation. Just, I'll just keep it on the side. So that find the first child which is not killed by rotavirus.
Mhm.
And then second step, I said this gamma is construct the canonical definition of FL with respect to its own restriction. And then
All
you
right.
do what mentioned concept. You restrict this with respect to this restriction of the parent.
Oh,
So
so actually, you first one balance it or whatever,
then you balance.
then you balance. So now you take this decision tree, which is
What do you mean by
Yeah, you chop off branches which are not consistent with local dot.
Oh, okay.
And then you unbalance. Sorry. Okay. Suppose there is a long path in the canonicalization tree along this direction A. Then how would you have gotten such a thing? That means there must have been an L in this range. Okay. So okay. Let's just say this is then there's a T1 which is between. Let's have a picture here. Gamma double prime. Right. This corresponds to F1. CDT of F looks something like this. It has the CDT of FL after that restriction and then balancing. And then the recursive part. Okay. Right. So this T1 corresponds to the length of this. So T is the
so now you want to prove that there exists a long path along alpha.
yeah.
T1 is what you had called the S.
T1 is what I call S.
So T1, okay, so now you look at the canonical decision tree for F with respect to rho prime. It should start with one of these lambda double prime.
Right.
Exactly. And now, when is alpha equal the restriction that you see along the A path? Well, you can definitely look at where where gamma double prime ends and where the rest begins. Now, why is the answer 1 there?
Why is the answer 1 here?
Because if the answer was
We only
if the answer was 0,
you won't have plugged it.
if the answer was 0, then I mean, if the answer was 0, then the and would be 0. I mean, we've chosen exactly this particular subfunction so that the answer is not 0. So the long path, so there's a path that ends in 1, right? And if it ends in 1, then it's made out of one path along all subtrees because those are the ones you extend. Okay, good. So you can look at where it ends in F. Right. Good. Yes.
And
And T1 is where it ends.
even is very comes. So yeah, let's call it as this is the restricted step. So you are taking this restriction tree and then applying a further restriction.
Yes.
You start with gamma and further restricted. So in this process, suppose the original gamma might have had some U1 many star variables. This only had T1 many star variables. Right? So there exists some U1 and perhaps and V1 belonging to 0 onto the U1. Such that V1 restricted.
Beta. Yes.
So you start off with this gamma and you restricted it and then you unbalanced. So if you take any one path in the initial segment of the decision tree, that would have a corresponding 0 path.
So the difference between T1 and U1 comes just because of the balancing.
The difference between it is coming because of the restriction.
Because of the restriction. But then shouldn't it be
There is a I mean U1 is a path of length sorry. There is a path of length U1 in gamma 1 becomes a path of length
T1 in gamma prime?
Gamma double prime. So
In gamma double prime. Oh, T1 is in gamma double prime. Okay. Yeah. All right. And the claim is also that T1, the first T1 steps are the same in gamma and gamma double prime. Is that also true?
T1 steps are same in gamma and gamma double prime.
No, because you could have removed intermediate variables, right? The variables that you removed when you further restricted don't have to be all at the start. Or am I wrong?
Okay, yeah. So we are taking a decision tree and chopping some of the branches. That means you'll be having some degree 1 nodes.
Yes.
What?
Degree 1 nodes in the decision.
But those you absorb, no? Or
yeah, that is the difference between this U1 and T1. So I'm only counting the degree 2 nodes in this.
Oh, okay. Cool.
right, but the T1 prefix does not have to be the same, right? As I understand.
Those degree 1 nodes will appear in this order restrictions.
Yeah.
But they will not be.
I see. So it won't be considered a prefix. It'll be there in beta, but it won't be there in the T1 part. Okay. I think I'm fine with that. Yeah.
Yeah, so
So beta is obtained by taking a prefix of alpha and adding some stuff in the middle. Right?
beta is obtained
By you take a prefix of alpha,
beta is a pivot of a prefix of alpha.
is a what?
Pivot, sorry, okay. Yeah, let's say this long path is alpha.
You
It's
take a
called
prefix,
alpha 1 is the prefix of
very good. And now you add some stuff in the middle of alpha 1. Oh, I see, no, a pivot of alpha, oh, I see.
Oh, okay.
With
This is
this
better.
prime, which is a pivot of alpha, and I extend beta prime with some extra stuff.
No, all these degree 1 nodes are in alpha 1 and beta,
Oh, they're both there.
but they take the same values in alpha 1 and beta.
So why do you restrict them? What does it mean to restrict? It means,
It just means some of the degree 2 nodes are becoming degree 1 nodes in the decision.
oh, but you don't shrink. The batch. Then U1 should be equal to T1. What's C1 then? I don't understand.
Okay. So okay, suppose you have this decision tree with the degree 1 nodes in it. Now all our different decision trees have degree 1 nodes.
The shape is.
If there are only T1 degree 2 nodes in a path, you only need T1 bits to follow that path. Now the depth is the number of degree 2 nodes. Depth of a path is the depth of a leaf is the number of degree 2 nodes along it.
Oh, I see. Oh, okay. I see.
And degree 1 nodes you don't have to specify. Suppose someone gave you a string of length T1. Okay, you go to the root node, look at the first degree 2 node you encounter, assign it the first bit of whatever B1 or the T1 length string, and then yeah, so okay.
So you are measuring the depth of a leaf with a number of degree 2 nodes.
Right.
So that is like shrinking the path, right?
Right. But for condition downward closure and stuff, we need to keep those variables in the.
Okay. Oh, all right.
Yeah, so yeah, the high level pictures you want to bound the probability that the big tree has a long path. You want to break it as there is a long path in the initial segment, there is a long path in the rest. Induction is going to take care of the long part in the rest path. Again, like in the previous proofs, there are three conditions. One is that the first chunk has a long path, the rest has a long path, and somehow the long path in the first chunk has some star variables or whatever. Again, you're going to follow the outline of the DLM proof. Again, you will have some preconditions there. Yeah. Okay. So, yeah. This is like saying this is like the previous. Okay. Yeah. And there is a queue which tells you which of these nodes are degree 2 among the other variables. Yeah, so going by the DNM group, we get these conditions that L is the first index which survives. Or another way of saying is if our prime is equal to is this is like the previous first condition. Beta said that
How about this sigma? Should be a sigma, no? What's this? How about the sigma? The one that witnesses.
so what sigma?
The one that witnesses that this guy is not one, hasn't been fixed to one. This 1B that we had in the previous book.
Yes, that is this beta.
Oh. It is,
So
oh,
sigma
I
is the
see.
zero bar.
Okay. So there exists a beta such that.
So previously also we had this long path, which is all 1 on 1. And
Yes,
for
yes,
each initial chunk, there is a
yes.
corresponding
So there exists a beta and a B1, by the way, right?
Yeah.
B1. Such that CDT B1. This is 0. Equals beta. Beta. Okay.
and then you would have this Q identifies stars of rotated vector within so F tilde rho tilde FL has more stars and rho tilde just set some of them. Q identifies in the domain of beta.
And then there's the
And lastly, we have this
vector.
part which talks about the rest. There exists alpha double prime such that CGP of A greater than or greater than T of F restricted with beta, where the variable is given by Q. Q identifies I'll just write it. So beta is this long path, and alpha 1 is the corresponding one path. Beta is the pivot of alpha 1, and that means they have same set of variables, they're querying the same variables. And right? Yeah, so there are a bunch of degree 2 nodes in both of them. Um, on the degree 1 nodes, they are the same. And the only place where they can differ is the degree 2 nodes. And there are T1 degree 2 nodes, and you are just setting those T1 degree 2 nodes according to this A. Yeah, that's just a way of saying, maybe I'm going to too much necessary technical details without properly defining what they are. That is just talking about the fact that the rest of the formula has a long path. Okay. Yes. Yeah. So this is the unpacking of this statement. Suppose there is a long path along this direction, along this of this shape A in the canonical dictionary of it. That means there's an L, which is the first guy which survives through that. There is T1, which is the length of the contribution of FL in the long path. U1, which is the length of this long path before the restriction, and B1, which is giving you the shape of the pivot, and Q, which is telling you which of these U1 variables are further restricted uh, according to Rotilda F. There's a bunch of data which yeah, essentially we are breaking this event into smaller inductive units. Okay. Yeah, there's this bunch of data such that these conditions hold. Yeah, now we're interested in this huge union bound. Union bound are all these data bits of this event happening. Right. Again, just like in the case of uh, we are coming from some lower close of restrictions. That is what we're interested in. Yeah, so just like in the DNF case, fourth condition is going to give us E log S by dt whole power T minus T1. Yeah, again, so we're going to factorize this into probability 1, 2. So we are going to get a factor of this much from here, and condition 3, which is talking about some T1 of them being stars, is going to give you a P power P1 factor, or rather some 2b by 1 plus b. And then you have this huge summation over this object, which when summed up, you want to get a P log s by d whole power T1.
So the P is not a problem.
Sure.
So the P is the beginning. Okay. All right. Okay.
Yeah.
Now you have to start thinking about this sampling procedure. No, this.
Now you have to start thinking about the sampling procedure. Yes. Yeah. So again, yeah, this is coming from a random pre-restriction, which is sampled by sampling a sigma and tau uniformly. Right. Right. Yeah. So this P power P1 sort of thing is again that neighborhood argument, which again we saw in Hastad's proof, and then the other proof. It's going to come there. And yes. So I just assume these two things and then show the convex P part of it, which is yeah. So again,
You're fixing what, an L T1? You're fixing T1?
yeah. Yeah, I think T1 can just sit outside from it's not
Now you want to show that this entire thing is the most log s by d to the d to the power T1. Right, so that sum with that probability of 1, 2.
yeah, some of the
And here you have to do something about it being informed.
yeah. The one thing which we are going to use about formula, which doesn't hold for the circuits, is that you have F and F1 to Fm are children of F. Then size of F is size of, and size is the number of leaves plus, which is, I mean, it's also fine if it's the total number of nodes. It's the class 1. Yeah. This is not true for circuits.
Yeah.
And this is what So,
I mean, there's between the sum of over t, there's that number, but right? Can you just erase the sum over t1? There's that, or put that number in between it or something. Yes. Now you want to show that this is at most log s by d to the dt1.
Right.
That L is the first index. Plus and b1 means
yeah, so
I guess you can union bound over b1, you don't care about that.
yeah, which is what we will be doing. Yes. This U1 is also will not hurt us eventually, but yes, there is one small thing which
Q again.
yeah, so I said okay, this factor is going to come from this term, and in the middle term, which talks about this condition 3, you won't actually be getting P part P1.
Okay.
You'll be getting a P by this is actually EF. So this P is just EF.
Oh.
Okay. Yeah. So or rather, okay. You can start with
Let me. Yeah, there you go. That's the division.
yeah.
Right, because
You are refining the PFL restriction to a P restriction.
will be restricted. So P is smaller, right?
Right.
Yes. Okay. Times P. Yes, that makes sense. Yeah.
Right.
So this is the additional probability that you need to put on the stars, so that you go from the restriction that you have on the child to the restriction that you have. The additional means that it's less than 1. The additional factor in the probability that you need to go from PFL.
Yeah. So I haven't mentioned what these PFLs are. So our final statement only has a P.
So that's PFL, right? This P.
Yeah, which is PFL. No.
Yeah, PFL.
Yeah.
I mean, oh, you mean you're saying you haven't set it? What?
Yeah. So for each node G,
Oh, I see. You haven't.
P tilde of G, I have to.
You haven't told us how you set these P's on the tree. I see. I see.
So you set them to be 1 by this criticality of actions. 1 by 10. Or rather, if what? SG is the size of G. This is 1 by.
It's not the criticality, it's the value that you want to prove about the criticality.
Yeah.
Okay, sure. So I see.
Or rather, I'm assuming F. This.
Okay.
Yeah, these. Yeah, so the tree of parameters is set according to the sizes and the depths of the corresponding subformula. Yeah, so now we are left with this 1 by.
So the P comes out and you're left with this 1 over
1 by PSL part,
PFL.
which according to that.
Oh, no, but wait, that P is not actually not P, that's P of FL, right?
Yeah,
The
this
one
P of
that-
FL,
Yeah,
which is this is.
that comes from the
of-
induction hypothesis.
But we are applying induction hypothesis on the rest of the this is again induction after some F.
Yeah.
I mean, technically it's the rest of the F after L. I mean, that's the niceness about. I mean, we are not looking at all the parts of the long path. We are just looking at the first part and the rest of the long path.
Oh, I see. So you're kind of doing what? Oh, I see. So you're saying, I see. So actually, right now, yeah, so it's like you have this outer induction that you're doing on. I mean, I see. So like, how many inductive steps you actually need?
Two times I am working induction. I'll be working induction twice. Once on this, then this looks like our hypothesis.
Right.
This
But
also looks like
at some point, there's only one, right? So you apply induction twice. What are you saying?
yeah, once on saying that the initial segment has so in the case of CNF, you only used once.
Yes.
But for general formulas, you use it twice. Once for saying that this part is small, and another for saying that this part is
Small or large?
okay. Large part.
I don't understand. So in the layout of the proof that you told us, you only use induction there, right? On point 4. So you're saying you also need to prove that, you also need to use induction to prove that the probability of 3 is at most that value, p to the t1 over p to the fl. Do you also use induction there? Is that what you're saying?
Where?
I only see one use of induction.
Okay, here.
Yes.
This is you see this.
That's the only one. What's the other one?
Okay. Let's see. What about this guy? This condition also looks like. Okay, now we are left with 1 and 2. So we are carrying this with us.
Oh, I see.
So yeah, so the way it would come in is
Okay. I haven't seen that.
yeah, these criticality statements, I mean the way they do like the bound looks something like this. So if you apply a random restriction, which is like 1/2 lambda, this number is going to go down exponentially.
Okay.
So here you're actually constructing FL decision tree at its critical parameter. And the reason for setting all these p tilde g's to be 1/10 lambda g is to achieve this inverse exponential sort of behavior.
Okay.
Yes. Yeah. Okay. Yeah, so now I want to claim that this condition has no Q in it. 1 and 2 don't have a Q in it.
They don't have a Q in it. Yes, that's right.
So you can pull out a factor of U1, choose U1 here. This will be L U1 B1. And so again, we use the same trick and write this as first as log 2 power B1 4 power B1 B1 power B1. Right. Let's give this a name. Let's call this new L1 B1 B1. The claim is that summation mu summation over L1 D1 these guys are not to 1. Right.
Actually, equals 1.
Equals 1.
I mean, there will be some L1 always. I mean, there will always be an L1, U1, B1, right? So,
Yeah.
so if you sum them, they should. These are functions of row tilde,
Don't do that.
right?
But yeah, so these are only the bad rows, bad row tildes.
The bad row tildes? What are the bad row tildes?
Bad row tildes are the ones which give you long path of length t. Or
Oh, I see.
this will just amount to the. You don't have all row tildes.
Oh, okay, yeah, okay. Okay. It sums to that probability.
This sums to 1. Now you have a.
Sorry, it doesn't sum to 1. It sums exactly to that probability, right?
It
To the
comes-
probability that there exists an alpha such
Yeah.
that.
Not quite. Here, we have dropped a bunch of conditions here.
Okay. But why do I care about those conditions, right? It's just, if I sum over all L, U, and B of the probability that I get this particular L, U, and B, I get in total, I get all of the probability mass that was there, right? Because these
Yeah.
are disjoint events.
Yeah, this is talking about this happening and more. This event is talking about these things happening and more. More things happening.
So for each alpha, which is bad, there exists exactly one L, U, 1, and B1, right? Exactly one.
Exactly 1. Yes.
Okay.
But
There always exists one, and there's exactly one.
Yeah.
So if I sum over all L, U1,
right. So there might be paths here which do not. I mean, it could happen that this is a path of length T1, but later on, this row along this branch A led to something small. I mean, this is only everything here, everything which is left is only talking about the initial part.
Oh, I see. Sorry, my bad. So you're saying, oh, I see. So, okay, so now you're taking a mu, I see. So now you're taking a mu, of course, I see. You're taking a mu, which could be a good one in that the path is short, but now you're just measuring the probability of having a 1 and a 2, meaning that FL is the first guy that isn't defined, etc., etc. And of course, that could be more than the band probability. But it's at most one, because the events are disjoint. Is that true?
Mhm.
Because, well, you define L as the first index which survives, and then you define U1 and B1 appropriately. Sure, okay, so it's at most one. Okay, sorry, I didn't get that. Yeah.
Yeah, so. Right, yeah, so. So what we actually have is not this, but this times 1 by TFL over 3.
Yes.
Right?
Mhm.
Yeah.
Mhm.
So which amounts to so let me write this whole thing maybe yeah let me yeah I'm gonna write this whole thing below, just U1 and B1 of this one.
Yes.
Right.
Indeed. Mhm.
Now let's now the whole goal is to upper bound that summation.
Right. Okay.
And furthermore, I just want to add that this new L1, yeah, L U1 D1, some constant here.
Okay. Each of them, because I mean each B1 is equally likely, right?
Yeah, B1 is of length.
Oh, but B1 is only of length. Oh, it's of length C1. Yeah, perfect. And each of them is equally likely. Right? Because by symmetry, let's say. That does it, right? That's enough. Okay, good.
So yeah, so now with this the rest of the application.
Okay.
Yeah, so now let's define this new L to be summation over U1 B1 mu of L U1. We're just averaging things.
Okay.
So in this language, this becomes
Always. Mhm. Mhm.
um, now
Now you do
we just want to
cavity.
concavity flow.
Yes.
So you get I'll write final answer. First, actually you would get this whole summation would go inside.
Yes.
Okay, let's try. From, that's just function. And we said that
That's at most,
that's,
yeah,
that's a little sum
it
16.
appears by all for one, it's exchanged for one, yes.
Yeah. And this dropping this b is going to give you a 2 power e1 in it.
Dropping this v gives you 2 power u1 again, yes.
And then you're summing over u1, that's geometric sum.
You're summing over u1. Sorry, what? Dropping this in u1.
Let's say this is from 8. Yeah.
What? Wait, why is it 8?
Uh,
It was 2 because the choices were. I see a 2, but I can't see an 8. Why is it an 8?
that where is this coming from?
Yeah.
That is actually coming from, if you look at mu, it is 1 and 2.
Yes.
Forget about 1, just focus on 2.
Mhm.
If you focus on 2, this is our reduction hypothesis
Oh, that's
with
the-
that parameter.
Oh, okay. Sorry. Oh, now you're using the induction. So it's not just a half. The half I could see, we could just by symmetry, but why is it 1/8? Apparently it makes all the difference, right?
Right.
So, okay, so now you're using the induction. And you're saying that, non-precision tree on.
This is just asking what is the probability that there's a path of length u1. I mean, this is roughly asking for there being a path of length u1 in F.
Ah,
When the random restriction is with that specific
P1.
that would give you a number like this.
Um,
So here it would be summation u1 1 by 8 power u1.
Oh, because of now you use your choice of P tilde of F.
Yes.
Of FL.
Yeah.
I see. So it's an 8 or 10. You're saying it's an 8 because you chose 10, but there's this extra 2 to the something that you're knowing.
Yeah, this will this 2 power u1 is going to get cancelled and is going to take away 1 2 from here.
Sure.
When you sum over all these, that will take one another 2, and ultimately you'll be left with something like this geometric sum, which is
How
just
much
a
is
constant.
VL? Why do I do that? The VL
That's a constant independent.
constant?
That's independent of equivalent.
Okay, okay.
Yeah. So my claim is at the end of all this, you'll be left with a constant here. With forward to one. That is actually 1 by TFL bar T1.
I see, so are you using the induction hypothesis like one? So in the CNF, what are you using? You're using that theorem that in order to get a zero, you need a very specific, you need a very specific setting for these variables,
Yeah,
right?
yeah, that's where you are getting this sort of factor from MCMF case.
Right. But now you need something stronger. Now you're saying sub formula, getting a particular path. Okay, wow. Right.
Yeah, so this is here again.
And I need to bound that thing by one, and you're done. Right, this thing that comes before the log, also,
Not one, but actually log s by log s by t plus 1 or d plus 1, what we should do.
oh. Oh, I see. Oh, now there's equals one. Okay,
Yeah, so there's some miss. Let's focus on this term.
actually, if we use the formula of f, then that b should be d minus one. Right?
Yeah, this should be d minus 1.
Okay.
Yes. I'm assuming it is d and the other one is d plus 1.
Okay, so let's say the formula of depth of the f.
Let's focus on this guy. Yeah. So what we have is this part d1. So let's focus on this. So now we are going to do this clever AMGM.
But what?
AMGM inequality.
Oh. Okay.
So I think this is upper bounded by so I'm thinking of it as d plus 1 terms, d terms coming from here and 1 term coming from here. It's a product of d plus 1 terms.
Factors, okay. D plus one factor.
Yeah. And this is like
Oh. Yes.
so let's plug this guy here.
Oh,
So what we have is summation of L mu L times log SL by mu L. There is one of the must be notes. There's a D. So there's D.
there's a D plus one. No?
I forgot about D. Yeah.
D
D
plus
plus 1. So by D plus 1 here.
okay.
Now we can use concavity of log bar T1, log bar d plus 1 times q.
Okay.
Say
Oh. Okay.
so I will not bother about this much.
Huh? No. You have to put it outside.
And summation of L SL is S. That is precisely where we are using
Yes.
that is point.
Wow. Okay.
That's the only point where we are using it.
Wow. That's some gymnastics.
Yeah, that is seems like a lot of gymnastics. Yeah, so there are several parts which came from. Is that some?
Oh.
Maybe I ran out of time. Yeah, so let's go back and then see what happened. Yeah. So there are several things which were used. One is the notion of downward closure, which appeared in the Hastad's proof. The other is the canonical relationship, which showed up, which is from the Rasbrough's encoding style of, and finally the entropic style gymnastics towards the end, which is coming from Rossman.
Wow. Damn. Cool.
Yeah, so we had this calculation. But we were sitting on this calculation for 2 years.
Yeah, exactly. So what's the story? So I heard it was quite a pain to figure out how to put all this together.
No, we thought we had proved 2 years back. 2 years back, we just couldn't argue. I mean, there are a lot of delicate things. There was some independence issue. Something we assumed is independent is not independent. Then finally we had to go via downward closure. So okay, before this, much of this follows Rossman's regular. There is a Rossman regular formula, X0 formula bound. Rossman shows the similar bound, shows the criticality of regular formulas as log s by d equal pardon.
Oh. What's a regular formula?
So regular formula is the fan at each level is the same. So yeah, so if you have a deputy formula, all the nodes here have the same fan elements and so on.
Okay.
Fan of a node is specified by the depth itself.
So why does that make this proof easier, sir?
So at least it doesn't make this proof easier. Rossman has a very ugly proof for regular formulas, which does not use downward closure. So here we used tree restrictions. For constructing canonical decision tree, we assume the input for the algorithm was give me a tree of restrictions, I'll give you a decision tree. So in his case, he expects a chain of restrictions.
Oh,
So if you give him a restriction for each depth,
uh-huh.
since all of them have the same critical, same
I see.
size,
I see.
so you hit them with the same restriction and then construct a decision tree.
I see. So the tree, I think.
Yeah, so what are the takeaways from this? I don't know. Yeah, so one takeaway would be,
Okay, how about unbounded depth formulas where you could maybe expect to go to quadratic signs?
yes, that is open.
That's the open question.
That's the open question.
Yeah.
So, yeah, so I think we believe that double closure is something which was not used there. I think, yes, I was not formal with many of these things here. Yeah, double closure. Sorry. Okay, so these are formulas of unbounded Fano and bounded depth. This is a depth formula. Fano would be arbitrary. So whereas you have De Morgan formulas, where Fano is 2 at each level. Depth could be arbitrary. Okay. So what do we know in this case? These are P by poly circuits. Right. We know that parity requires size n square by circuits of this kind. The best one around here is n cube for some modification of Andrews function. Yeah, so right. Again, this
Do people know correlation bounds against such
No.
formulas? No, and that's the point.
that's the point. Yeah, here in this setting, yeah, we don't know correlation much, and again, it's conjectured by Shankar that again, you apply, you have a De Morgan formula like this, you hit it with a random restriction. And ask what is the decision we get, or rather, what is the criticality of a De Morgan formula?
Yeah, yeah.
It's expected to be square root
Number of leaves.
number of leaves. In other words, it's expected to be square root of
There. Right. Got it. Okay, let me